So welcome to what is now our sixth class, right? At the end of last class, we took a bit of a survey as to the area of interest. You know, if I define roughly three components of data analytics, one being interactive visualization, one being probabilistic modeling or statistical method, and the other one being sort of like a more modern machine learning based method. I think most of you were interested in doing analytics using machine learning. Okay. So, but having said that, I think like I told you that last week, it's not a preference, right? Decision between statistical method versus more modern method like neural network. It comes down to the fact that it comes down to the nature of your data, right? So if the nature of your data warrants statistical hypothesis, it would be silly. In fact, it would be foolhardy to use machine learning, right? So if the data is amenable to performing, say, linear regression, and you would just say, okay, I'm going to use neural network or, you know, a deep network or, you know, random forest, it wouldn't really make much sense, right? Because you would have a lot less rigorous framework, a lot less theoretical foundation for that. So it's not a matter of preference, right? In a way, it's dictated by your data. Now, of course, as a class project, it could be a matter of preference because you haven't yet chosen your data set. Okay. So anyway, what I've decided then is that as most of the project will be based on machine learning techniques, I think I'm going to start teaching the sort of like, you know, start from things like decision tree all the way up to neural network. I'm going to have that start maybe next week. What I'm going to do this week is actually just one class, dedicate one entire class to nothing but probability and statistics. Okay. To emphasize the fact that it is important, I'm going to base a lot of the midterm exam on probability and statistics, because after all, other techniques, you know, machine learning technique based kind of thing will be appearing in your project, right? So the midterm will be mostly two things. One is the interactivity, you know, using manipulate and whatnot in the Mathematica, and doing probability and statistics, traditional or classical traditional statistics. Right. So let's get going for today. So today is all this. Okay, today is all this. So tell you what, let me move it over here. So yeah, that looks a bit better. Yeah. And let's start to expand it. Okay. Right. Okay. Now, again, what's the difference between, you know, probability model and inferential statistics? One analogy I like to do is, you know, to say, pretend that, you know, we're playing God. It's like God sets the rule for how things happen. That will be the probability model. Okay. And if nature conforms to that, if the data has the distribution in accordance with my desire, so I'm you know, data God, I declare that the distribution of male population or female population or this kind of genetics, all kind of distribution, I make the decision, okay, it's going to follow this probability model. Okay. And then I let the world run. So the data is going to be based on that, right? So I'm kind of like running the simulation, okay? So I said, this is how human beings' heights would be distributed. This is how the age distribution will be, right? And I just, boom, by magic, just say, okay, this is the probability distribution of human age and sex and blood sugar count. I don't care, whatever, okay? That would be implicit, right? That's like the hidden answer, okay? But you, as data scientist, you don't get to know that. So you're trying to guess what my mind is. You're trying to guess what I did. So you're trying to work backward from evidence of the data. So sometimes there's some clue, right? So if the data is always positive, then you can't use distribution that has negative value. for example. Okay, so this is a kind of obvious rule, but with experience, you come across a lot of sort of like shortcut or sort of like a mental shortcut that you can help that can help you formulate. But anyway, eventually you decide on maybe this kind of probability model, and then based on that, you run the data to fit the model, by which I mean to get the parameter of the model from fitting the data, and that would be the statistical inference, right? Now, today we are going to go both deeply into the probability side, the creation of randomness, and statistics, the inference of what the underlying nature of randomness is. Okay, so that's basically the name of the game for today. Okay, name the game today. So now here's the thing: probability. I've kind of like taught this for many years. What I like to do in this mind map here is sort of like separate into two chunks. One is the foundation concept, meaning if you're going to understand what we mean by probability, analytical probability, not like, I have a probability of being sad tomorrow or something like that. Okay, that's kind of like casual sense of probability. It's probably going to rain. I'm 50-50 about whether or not to buy red shirt or blue shirt. That's a kind of like colloquial way of talking about probability. But we talk about rigorous analysis of probability. What are the foundation concepts? And then I'll go to the probability distribution. This is where I sort of like spell out what kind of function, what kind of probability distribution function mathematicians over the past 300 years have come up with. And like I alluded to last time, there are hundreds of them, in fact, thousands of them, I'm pretty sure, okay? But I'm actually going to tell you that there are about 10 of them that really matters in your life, okay? Sometimes there'll be some exotic probability that matters in your life if you work in a special area, but that just means that when you go to that kind of job, they're going to teach you that special probability, okay? But the probability sort of like ubiquitous, universal probability, they're about a handful. I'll just say 10, okay? And these are the ones that I will be asking about during the exam. Okay, so the exam would be something like, by the way, each of you will have different data set based on your student ID. Okay, there's going to be some kind of randomization. You'll be taking tests on the Mathematica notebook. So all your data will be different. And then you'll be asked, okay, what kind of distribution should I guess? It's all positive. You can't use normal distribution or that sort of thing. Okay, right. So what are the foundation concepts? Okay, what are the foundation concepts? The most simple thing is, and this is very important, right? Random events. Random events. That's it. This is something that has nothing to do with mathematics. It's just something that you don't know what's going to happen in the future. It's random. Okay? It's random. So here's the name of the game. Okay? When you say you don't know what's going to happen, that's beyond probability. Probability in this sense, you know what could happen. You don't know which of the possibilities. All right? So if I pull something out of the bag and I ask you, what could this be? You have no idea. That's way beyond probability. Okay? That's just like you don't even know what's valid. Okay? Anything that fits in the bag. But if I say something like, I have a dice, and that dice has 6 faces, and I toss in the air, yes, that becomes probability, because you don't know which side it's going to land, but you know the sample space or the possibilities, okay? So the most important understanding is probability begins with possibilities. Okay, so the unknown, that's beyond probability. Okay, it's the unknown known, meaning you know exactly what could happen, just not sure which is going to happen. All right, so that's very important, and those are called random events. Now, random events are not mathematical by nature, right? For example, if I toss a coin, it could be head or tail. Intrinsically, that's not mathematical, right? Now, right now, all I want you to know from random event, that the key concept that's going to get everything going is basic event. Okay, basic event. So basic events are sort of like something that's very specific. Okay, specific. And then compound event. Now, certainly this is a little bit like what's the basic unit of life? Is it atom? Is it molecule? Well, certainly if you say the unit of life is atom, right? The composite is molecule. If you think the basic unit of life is molecule, the composite is protein, right? So there's a layer of where you decide what's the basic, what's not basic. Okay, but I'll give you an example of something that seems kind of obvious, right? If let's say I toss the coin 3 times and I get head, tail, tail, okay, that's specific. Now, if you know physics, or well, you don't have to know physics, head, tail, tail is actually not that basic because there's so many ways you could get head, tail, tail. But if I define head, tail, tail as basic, okay, as basic event, and I define compound event as 1 head and 2 tails, you can see why 1 is a compound event, because you can have more than 1 basic event. So if I toss head, tail, tail, it is a 1 head, 2 tail. If I toss it as tail, head, tail, it's also a 1 head and 2 tail, right? And finally, if I toss and it's tail, tail, head, that also counts as 1 head and 2 tails, okay? So without getting to mathematics yet, okay, you realize that the probability of compound event, if you define it this way, okay, the basic event adds up, okay, but they don't overlap. If you have head, tail, tail, you don't have head, tail, head. Or sorry, if you have head, tail, tail, you don't have tail, head, tail. Okay, so it's not the same event. So let's say you have probability of head, tail, tail. You have probability of tail, head, tail. And you have probability of tail, tail, head. Okay, now you might jump ahead and say they should be the same. Forget it. Doesn't have to be the same. It's A, B, and C. My question is, what's the probability of 1 head and 2 tail? You should be able to add A, B, and C, right? Because basically the component basic event contributes probability weight. Okay, so that's like the most basic way of thinking probability you can think of. Has nothing to do with, well, it doesn't get to the level of mathematics yet. Okay, but that's very foundational. We'll get to that. Now, with that, the way that there's a branch of mathematics, and this is a bit of a side note, called combinatorics. Okay, combinatorics means a way of combining things. What do you combine? You combine basic event into compound event. So if you have probability of head, tail, tail, and tail, probability of 1 head and 2 tail is adding them, right? Who is good at this sort of thing? Well, obviously mathematician. Okay, how can you make money of this? You go to Las Vegas, right? But you better be, you better be very have a separate skill, which is a disguise, because they'll watch you. If you know how to count card, have you heard that term? Counting card means everybody knows what the basic probability is. Basic event, probability of basic event. Probability of a given card is 1 out of 52. Probability of a given sign is 1 out of 4. Probability of one number is 1 out of 13, right? That's basic events, right? But if you're going to add into blackjack or something like that, this is a combination, right? How many combination of basic event adds up to 21? Right? And how many is already out there on the table, and so how many is left, and that sort of thing. And this is what counting probability is, called combinatorics. This is actually the most basic way of thinking about probabilistic thing in life. Okay, fine. So we haven't got to the mathematics yet. We can't go on without mathematics. So let's see what happened. So I talk about events. Let's talk about probability. Okay, so probability. Now, I'm not gonna talk about this right now, but let's say everybody has an intuitive sense of probability. Actually, I'll talk about it. If I ask you, what's the probability of rain today? Or tomorrow, let's say tomorrow. Okay, tomorrow. What you might do is actually look at typical rain probability for the month of September, right? Okay, so that's kind of like a probability, but it's a very fluid thing. It depends on a matter of information. So if I said, aha, but I just read in the news that there's a storm in Canterbury, not in Bangkok. Canterbury is kind of like 3 hours away. Okay, you might revise that figure up. So this kind of fluid meaning of probability is actually what human being means by probability. It means likelihood of thing. Okay, and it's a very fluid thing. It's a matter of information. And tell you what, and you probably don't believe this, but this very commonsensical way of probability is not the way for 300 years most people have taught probability. The way they think about probability is frequency. Now, frequency in this case, it would be something like out of 1,000 September, how many, you know what I mean? How out of 1,000 September 13, okay, how many times would there be rain? In which case, the population of September 13 goes all the way into the future, right? So this is why they have this idea of population, right? And what about past September 13? That is sample, right? So even though your idea of probability is the likelihood of stuff, the way we work with it analytically, we have to think of it as some kind of population and proportion of a population. Proportion of September 13 that has rain versus September 13 that has no rain. And then past September is not information, but it's a sample. Right? Special kind of information. It's a sample, and then you make extrapolation. Now, these two are in a way, I'm not going to spend too much time on this because in practical term, people will always do analysis in this kind of frequency mode. But when they think about it, they will always think in terms of likelihood mode. Now, when I was your age, these two camps of statisticians are very separate. You know, it's like they have academic fights, okay? One believe in this kind of frequency probability. They are called classical statistician, okay? Those who believe in a more commonsensical information fluid way of probability is called Bayesian statistician from a mathematician named Bayes, okay? So this is kind of like a philosophical, and they kind of like fight, you know? Well, it's not a bloody fight, but it's academic fight. Okay. Now, let me tell you this. For the past 300 years, this is the classical statistician. People think in terms of population data are the mainstream. Okay. So the Bayesian are the hippies, sort of like outsider. Okay. However, when you move to things like machine learning, you know, all the way up to large language model, it turns out that the way modern machine learning operates is more like Bayesian, because you update information as data comes in. There's no big population. There's no general population. There's just sort of like, you just keep winging, well, not winging, you keep adjusting probability based on your additional information. So it turns out that for the past 300 years, these are the mainstream. I think in the next 300 years, these guys will be the mainstream. Okay, that's just my guess. I don't know. Okay. Anyway, but here's very important. Doesn't matter. We have to agree on one thing. How do you represent probability? And how do you represent it as a number? You represent it as a fraction of 1. And this is something that nobody disagree, right? It's always, okay, so this is what's called axiomatic definition. And this is kind of the rule of the game. So I can't say probability of 5. Nobody, okay? And this is why when you see somebody who wants to tell you to bet, oh, you know, buy this stock, I'm 1,000,000% sure. It's nonsense. You can only be 100% sure, okay? So the probability axiom, did I get it out? For any event A, and this event can be compound or basic. Any event, probability is greater than or equal to 0. In other words, there's no negative probability. Okay. Number 2, this thing about, I told you about, you don't know, you don't say, I don't know what's going to happen. You know what could happen. You don't know which one is going to happen. But the total set of possibilities, that's called sample space. That's all there is. Nothing beyond that. Okay. So that sample space, the probability of the entire sample space is the probability of all possibilities, right? So by definition, that is the highest. We set it to 1. Okay, we set it to 1 or 100%. So you can't be 100% sure. Okay, you can only be 100%. I don't know if you can give 110 effort. Maybe effort you can borrow from the future. I don't know. Take a steroid or something. Whereas the opposite of sample space is empty set. Empty set means impossibility. What's the probability of impossibility? That is equal to 0. Okay, so something that is impossibility is something that has 0 intersect. Okay, so if you're a human, you cannot be a dog. Okay, so in this world, there's no human dog. So the probability that somebody who walks in is both a human and a dog is 0, because the set of dog and set of human don't intersect. Simple as that. Okay. Now this is just a baseline rule of the game. But then there's some thing called, you know, measure theoretic foundation. Essentially, it's that idea of adding probability. Okay, it's the idea that you can add probability, and if they're disjoint, if they are disjoint, if they have overlap, then you have to not double count the probability, that sort of thing. Okay, so for example, if I say what's the probability of a boy or someone who wears pants, that probability is probability of boy plus probability of someone wearing pants, right? But then you actually double counting boys who wear pants. So you have to subtract that. So this kind of additive rule, this is kind of built in, okay? Now, you know, this is, you can be rigorous. Sometimes you need to be rigorous about this, but for our class, we kind of moving very fast. So sometimes I'm going to go very fast. Now, here's where we come in, and this is where the perspective is very important. Again, Basai student is not just about understanding the mechanics of mathematics, but understanding why the mathematics, right? Not how to do this calculation, but why this calculation. Here's the name of the game, and you have to believe me in this. Mathematics allows you to do all kinds of stuff in terms, and what do I mean by all kinds of stuff? Analysis. You can analyze things, okay? So if probability stay as is, like this, probability of a head and tail, fine. You can sort of like, roughly speaking, add numbers, but you can't do much more. You have to translate probability world into mathematical objects. And how do we deal with mathematical object? We have function, variable. Okay, or if you want to be more detailed, function, variable, parameter. We talked about it last time. Okay, so the most clever thing is you can't do much with probability until you turn it into mathematical object. So there has to be a dictionary of turning events into numbers. That's it. That's it. You can't analyze event with math. I can't say probability of apple. Okay. I have to assign some number to that. That's why you start assigning number to it. So instead of saying probability of head is 0.7, I had to say head correspond to the number 1. Tail correspond to the number 0. Okay. So you would see now, just listen to me carefully because I don't want to go back and forth between this thing. It takes too long. The language they would say is this: let X, big X, be a random variable. The word is random variable corresponding to the outcome of a coin toss. Okay? Corresponding to the outcome of a coin toss, where head correspond to 1 and tail correspond to 0. Okay? Actually, this is a good time to go to paper anyway. So let me do that. No, not quite. It has to be I have to share this one. The same. Yes. This? Yeah. Oh, okay, gotcha. No, I want to use this. Yeah, no, it's okay. Okay. Focus. It's not a focus. Not one thing is the other. How do I do this? Focus. You're supposed to check this before. Yeah, the focus. Nope. That's good. Yeah, next time make sure you cut this in there. Yeah, whatever. Yeah, make sure you have this. Okay. So X, can you see that? That's a big X. Oh. What? Can you guys see that? Okay, so maybe that works. Okay, something like this. This is how you write, okay? Okay. So let X be random variable. Okay. Okay. And then you write this. Probability, okay, that X equal to 1 is equal to, let's say it's a little bit of twisted coin, something like 56%, 0.56. Okay. So whereas P X equal to 0 is equal to 0.44. Okay. So this is how you would write it. So X is a random variable. Now this is something I'm going to ask for the final exam. I can tell you, I ask this probably shoot every year. What's wrong with the name? It's not random. Because every time I get a head, it's a 1. Every time I get a tail, it's a 0. And it's not a variable because it's an assignment. So it is a function. So even though it's called random variable, it is a deterministic function. It's a function that gives number associated with random events. Okay? So random variable is neither random nor a variable. But why is it called random variable? Because we will use it. This value here, the value here, okay? This little value here, I'm going to write it generically as this. Probability x is equal to little x. Okay? It's equal to p, little p. Now, so have this bird in the back of your mind. In reality, probability x equal to 1 is equal to 0.56. Probability x equal to 0 is 1 minus that, right? It's 0.44. The way we write it is P, this stands for probability. So this, read with me. Probability random variable x, okay, takes on value little x is equal to P if x is equal to 1. Little x equal to 1. Okay? And then 1 minus P if x is equal to 0.มันไม่รู้มันเหมือนโฟกัสไม่เคยได้มั้ยได้มั้ยได้ยังได้แล้วแค่นี้แหละคือเดิมมันไม่ได้ผมก็เลยมั่วเอามันไม่ได้ทั้งหน้าแต่ไม่เป็นไรได้ครึ่งหน้าก็ยังดีโอเคมันต้องยืดแล้วโอเคให้มันเห็นทั้งหน้าแล้วโฟกัสเนี่ยทำได้ไหมถ้าได้ก็ดีถ้าไม่ได้ก็ไม่ว่ากันโอเคแล้วโฟกัสไหนokay so why is the bottom line important? Why is that important line important? Because now I'm going to take little x here as my variable. And the right-hand side is my function. Okay? So this little trick here of turning event into a call-out table. If I see a head, I will call 1. If I see a tail, I call 0. This little trick here allows me to work on head and tail, but in mathematical function form. Okay? So that's the name of the game. Okay? So now, I'm going to write something that's the most confusing statement you will ever see for the rest of your life. Yeah. Yep. Okay. Tell me if this doesn't look confusing. But if you make conception, you make the conceptual link on this line, you'll be okay. Okay. Look at the middle. Probability x is equal to little x is equal to p if x is equal to 1. And 1 minus p if x is equal to 0. Now, with my coin, what's p? 0.56. If I take another coin, maybe it's different, right? That coin may be 0.501. So what is something that can change across different contexts, different problem, but it's a constant in the same problem? It is parameter, right? So in this case, left-hand side here is a function. In other words, if I'm going to write in a mathematical form, it should look like this. F of x given little p. Right? Okay? It's a function of little x depending on p. Okay? Why would I do this? Okay? Again, I'm riding an elephant to catch a little dragonfly, ขี่ช้างจับตั๊กแตน or catch a grasshopper. Okay? Why do I do this? Because once I have this in place, this thing can get messy as much as I can. This thing can be as general as I can. This thing can be as messy as I can. Right? Does that make sense? And this is why I say that there are the set of all x can be finite, countable, bounded, semi-bounded, unbounded. Remember the Wikipedia page? And if it is finite, then you have F. And there are how many of them? 10 of them. Okay. So you understand the game? Okay, understand the game? I turn event into numbers. So basically, I can define a function on it. And to define a function on it, before I just go ahead and say f of x, I say, what value can x takes on? Because in probability, you know what it could be. You don't know what it's going to be, right? So I know that my little x can be positive, but not negative, right? Can be any number, doesn't have to be discrete. Can be 1.7, can be pi, can be e, can be 1.7 times e, I don't know. Can be anything. So what's that going to be? That's going to be semi-bounded, right? What if I say my x is a score of a student between 0 and 100, any number, continuous number, but between 0 and 100. Well, 0 to 100, if you divide by 100, that's like 0 and 1, right? Okay. Anyway, it is bounded. Okay. Now, if x is exactly the number of dots on a dice, and there are six sides to a dice, 1, 2, 3, 4, 5, 6. What is my set of possibility? What's my sample space? Finite, right? 1, 2, 3, 4, 5, 6. Right? What if number of lightning in a given day in a city? Well, it has no upper bound, right? But you can't have half a lightning. You can only have 0, 1, 2, 3, 4. So it's discrete, right? But no upper bound. What is it? Countable, right? So this thing. Now, so that's why, okay. Let me see if I can do this quickly. I'm getting better. Nope, I have to do this. Time. Okay. So there. So I have to assign number to an event. That's the concept of random variable. Okay. So the concept of a random variable, that's what we talk about. Now, another concept, okay, by definition, by type, and we'll say, okay, by definition, it's neither random nor is it a variable. Okay. By type, well, what kind of random variable can you be? Well, you can be discrete, right? So this is what we talked about earlier, right? So it can be discrete, so it could be number scale or right? So nominal scale, ordinal scale, finite set, blah blah blah. So this is where you get this thing where it's finite, countable. Okay, this is number scale. I talk about it because it is very important to talk. But let's talk about the number line. It can be finite set, countable, right? In this case, bounded, semi-bounded, and unbounded. So finite, countably infinite or countable, bounded, semi-bounded, unbounded. 1, 2, 3, 4, 5. 1, 2, 3, And this is something that's, I'm actually going to put on exam. It's, again, I'm struggling with what I can test you guys with on an exam basis. And this is obvious, right? So I've said, set of, let X be a random number corresponding to the number of times you get yelled at in a day. Okay? Could it be negative? No. Can be 0? Yes. Can be half? No. You can only be yelled at. You can't be half yelled at, right? So 0, 1, 2, 3, 4, 5. Well, maybe, there's no upper bound. Certainly you're not gonna get 5,000, but the point is you can't get an upper bound. If you can't get an upper bound, technically it's infinite. Okay, although you'd be very unlucky if you get 1 million yells at you or something. Okay, so this is the sort of thing that's I can ask you in the exam. So that's the random variable. Now, what is once you have the definition, before you go to any kind of fancy mathematics, the most obvious thing you can ask is what's the most likely value you're gonna see, right? And that corresponds to the human concept of average. In all this, whether or not it's called average, it's mathematically, it's called expectation. Okay, so what do I expect? Okay, now here's the thing. Expectation is a funny number because it doesn't belong to the same sample space. What do I mean by that? How many children can a family have? 0, 1, 2, 3, 4, 5, 6, 7, 8, up to infinite, right? So it is countably infinite. But when I talk about expectation, Thai family I expect a typical Thai family will have 1.7 child. You cannot have 0.7 child, but expectation or average, you can, right? So you take this kind of expectation, this kind of average, it's like the first statistic human being comes up with. Okay. I went to well, I didn't. I got caught COVID. Say I went to Copenhagen. Copenhagen has one of the tallest people on earth. Actually, the Dutch, but let's say I went to Netherlands or something. Okay, you say, well, how tall are they? I would say, well, there are about 1.8 meters on average. Right? That doesn't mean there's one guy who's doesn't have to be one guy who's exactly 1.83, but on average, they kind of like add up and divide by the number of population, you get 1.83. So this kind of mean, this kind of average is the most basic statistic you will deal with. Okay, fine. So that's the concept. So we go to, oops, again, I'm on the wrong screen. Okay. Yeah, so expectation. Now, last week, we actually went to an orphanage in Pattaya. This is a faculty outings. It's really funny because when the kids came out and greet us, they all have the same height. I don't know why. It's kind of weird. It's just a funny thing. They're kind of like this tall. Okay. So what if I say on average, they're about this tall, but that have very short and very tall, and another group of children who's very homogeneous, low variability. Okay, so that's the second thing I would notice. Okay, first thing I would notice, well, these are tall people. Okay, second thing, after noticing that these are short children, I would notice, hey, not only are they short, they're almost the same height. It's like and maybe they take them by size or something. I don't know. Okay, whereas another school, you have short children and tall children, same average. So what's the second statistic you're going to be concerned with? Variability. Okay, variability around that means. Okay, so keep that in mind. Two things very important to you. Okay, so once again, you turn random events into number. When you observe that number in real life, you can observe 1,000 number. You can't report 1,000 number, so you can report one number. What would you report? You would report average. What's the second number you would report? It's whether or not that people are near the average or very highly variable. Okay, it's called standard deviation, but come to that later. Okay, but the general concept is called central tendency and dispersion. Okay, so this is how you characterize a population. Okay, this is how you characterize population. Think of it as if you are a tailor, right? You go a population and low variability, you just make one size shirt. But same average height, same central tendency toward 1.8 meter, some tall, some short, then you have to make many sizes, right? That sort of thing. Okay, so that's a statistical thing, eh? Now, and this is where, oops, I'm actually in the wrong page again. Oh, I have to do it on here, right? No, I should do it here. Can I make full screen? Sorry, yeah, make it full screen. Yeah, you don't need to view the. So that's a concept of expectation. Okay. So we'll get to this, but it will be a concept called variance, but I'll come back to that. Now, this is where we talk about distribution. Okay. Now this is I'm going to give you this, but you are not going to be able to climb through all the branches, but basically this is what I plan to have in my books. But okay, let's count them with me. Okay, 1, okay, 1, 2, 3, 4, 5, 6. Okay. Now, after you got 6, sometime you would go here and say 7, 8, 9, 10 or something. But basically, these are sort of like the 10. 1, 2, 3, 4, 5, 6, 7, 8. Oh, sorry. There it is. 9. Okay. Yeah, about 10. Okay. So let me just give it to you right now. The reason I have 2 here. Oh yeah, I know why it's 10 because I count this. Okay. This is a special case of that. This is a special case of this. This is, I don't know why it's, yeah, it should be here. Weird. Okay, I think I kind of messed it up somewhere. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, and 9, 10. Now, these 2 are so ubiquitous that even though it's a special case, I want you to know by its special name. That's all. Okay. So they're about 10. Okay, fine. Mixture distribution, this is a little bit tricky. I won't teach you, maybe I will, but I won't. Okay, multivariate distribution, that would mean something like if you have combination, right? So it's not just one random variable, but 2 random variables that are correlated. They're not independent. What is the most ubiquitous? Multivariate normal. Okay. So tell you what, let's can we mark it with color? Okay, 1. Forget that. That's a little bit 2. Well, anyway, I'll come back to it. Sorry. Okay. Now, before I go to Mathematica, we're going to show you how this all works out in Mathematica, right? Well, actually, let's do that right now. Okay. Okay. Probabilistic modeling. Oops. Okay, that's under chapter 4. Okay. Now, that concept that I was telling you about the mean and central tendency and dispersion, that is sort of like, I wouldn't say primitive, but it's sort of like statistic without much math. You don't have to do any kind of hypothesis testing. You don't have to do any kind of fitting distribution. It's sort of, you just take a data, right? And what's the average height of people in the dataland? Well, maybe you gather 100 of them, add all the height, divide by 100. Okay, so this is a statistical way of getting information that's very basic. So you can think of it as calculator kind of statistics. Okay, the proper word for it is descriptive statistics. Okay, so the kind of thing that you can describe with this basic, calculator or spreadsheet, we call it descriptive statistics. And that sort of like gives you a rough idea of where the distribution is. But you're not actually trying to get at the functional form. Once you get to that stage where you try to fit the F given the parameter and get the data and all that, that's called inferential statistics. Okay, so you infer more information. That's what it means. Okay, so right now, the basic thing that you have to do to get by in life, just describe stuff. Okay, how tall are people in the Netherlands? Well, 1.83. How do you get that? Well, you sample 1,000 people and take all the height, divide by 1,000. Okay, simple as that. Now, for that, okay, I'll give you this notebook so you can double click on it. So there's a guide on descriptive statistics in Mathematica, and then you can, it's almost like a self-learning thing. Okay. And again, I should not have to spend too much time on descriptive statistic because, okay. So go to that page if you like. Okay. Now let's move on. Let's go quickly. We don't have time to, oops. Okay. Right. So basically, the thing you need to know is mean. Mean is basically an average, okay? So in Excel, you say AVE, RAGE, right? Here you use the word mean. Okay, that's it. Sometimes you use harmonic, never mind. Harmonic, geometric mean, these are also very important. Sometimes it matters. Now, yeah, maybe this is what you should do. Because my book is going to be fairly comprehensive, right? It's going to have all kind of stuff, but pay attention to what I say as the basic set, the basic toolkit, what you need. You need to know, maybe you don't need to know harmonic means, okay? In engineering, you might do. Geometric mean, you need to know that if you're in finance, but for everybody else, you need to know two things, mean and median. Okay? Mean is you take everybody's, okay? Takes everybody, okay? Add them all up, divide by the number. So it's, mean is an average, basically. Mean is called arithmetic average. Okay? You need to know that. Median. What's median? Median is when you line them up and you take the guy in the middle. Okay? That's it. Oops. Okay? You take the guy in the middle. Why is that important? Because the distribution, think of the income cap in a lot of country, right? If you talk about this country, what's an average GDP per capita? Oh, it's, rich country. But this country actually has all of you and maybe one Jeff Bezos or something like that, right? Think about that, right? Everybody is around here, and then there's like billionaire over there. Well, he ruins the average because the average looks good. Everybody's a millionaire. So a more representative when you have something that's very skew. And in life, you get a lot of skew data. You will say, hey, what's the guy in the middle? It turns out the guy in the middle makes 20,000 baht a month or something like that. Okay, even though you take an average of the whole country, you have very rich people. Okay, so the two central tendency that you need to know are mean and median. Okay, geometric mean if you are a finance student, harmonic mean if you are engineering, but never mind. Okay, fine. So again, I'm just making something up. So mean of the data, so the data, right? So the means. So median, skip the guy in the middle. What's this here? Okay, never mind. This is all detail. Right. Now, the second thing you need to know is dispersion. Again, that orphanage that went to, everybody's about the same height versus, a more typical classroom where you have short children and tall. When I was young, it was always like the shorter ones. Okay. You need to know standard deviation and variance. Why don't you know other thing? This is kind of historical. Okay. Once you know the distance, the average height, okay, how much do people differ from that? So there's some taller people and shorter people, right? So what you would like to do is take the distance. So if the child is about 3 feet tall, somebody who is 3 feet and 1 inch, the difference will be 1 inch. Somebody who's 2 feet and 11 inch, the difference is also 1 inch, right? So basically you want 1 inch and 1 inch, okay? And take an average of that. That's called mean absolute deviation. Why is that not something you hear? In fact, some of you may, as basic as it is, may have heard it for the first time this year in this class. Because historically, in order to do this, you have to say, if x is greater than mean, take x minus mean. If x is below mean, takes mean minus x. That is a computer algorithm. And if you had to do this 200 years ago before computer, it's very tedious. Think of it that way, okay? Whereas mathematically, you have one recipe called standard deviation. That is to take the difference, square it. In that case, you don't have if then. You have one rule, okay? So if it's taller, square it, you get a positive number. If it's shorter, square it, get a positive number, okay? So in a way, when you do this and take an average, that's called a variance. So the reason variance is the basic unit of dispersion and not mean absolute deviation is because mathematics came before computers. Okay, so this is historical thing. Okay, fine, no problem, no problem. But then your units are wrong because it's square. So what you do is you take a square root of that, and that becomes standard deviation. Okay, this should be old news. So you should know standard deviation. Okay, you should know variance. Now there's this thing about, degree of freedom, why you divide by n minus 1, that's kind of detail. Range is another thing. Well, range is useful because if I don't want to just know how tall people are in the Netherlands, but I'm in the business of making a coffin or something, okay? So definitely I want to know what the maximum is, how the tallest guy and the shortest guy. Well, the range between tallest and shortest is a range, right? Now, of course, you can say, well, if somebody is really tall, I can build a special coffin. Okay, I just want to make the range of coffin that covers most of the population. So a nice concept is called interquartile range. That would be like line them all up. Don't take the middle. Take the guys a quarter of a way from the shortest and quarter of the way from the tallest. And that's the range I should work with. Right? And if I make coffin in that range, I can satisfy 50% of the dead. Okay? That makes sense, right? So in that case, I'm not so much concerned about the individual variability. I just want a maximum and minimum. Okay, so you can do that. So in this case, you might as well know all 5 of them. Mean absolute deviation is becoming more relevant because it's with computer, it's just as easy to compute it. Okay, now here's where it gets interesting. Remember that variance, you take a square, right? That means whether or not it's bigger or smaller, it contributes to the variation. What if I want contribution that has a sidedness? In other words, more than the mean versus less than the mean. I can't take even power. I take odd power. So I raise to the power 3. When I do that, an average of the difference to the power 3, that's called skewness. The reason that would happen is it would emphasize the long. So if I have, okay, look at my, maybe I should do this. So this is a distribution of income. You have a lot of poor people or middle income and very few rich people. Okay. If you think about it, the mean is somewhere here, but the median is all the way here, right? So this kind of distribution is kind of like lopsided to the right. This is called positively skewed. Okay. And when you take this, if you have a data and the histogram looks like this, you find the mean, you find the individual difference, take to the power 3 and take an average of that, you will get positive number. It's called positively skew. Okay. And then you have this thing called kurtosis, which is to raise to the power 4. That's sort of like how spread out things are. Never mind. Okay. Now, these are the 4 concepts that are important to descriptive statistics. What I mean in this case is that before you can send a fax. I'm in the Netherlands right now. I'm trying to describe the population, the high distribution of people in the Netherlands, right? I don't have a fax. I don't have a telephone. All I have is a telegram. Think about this. This is very primitive, right? And telegram is very expensive. I can only send like 1 word. What would be the first word I would send? I would send the mean, 1.83. Okay, what's the second word I would send? I would send the standard deviation, how much they vary around the mean. Okay, now, if I have the luxury of 3 words, what's the third word I'm going to send? Skewness. What's the 4th word I'm going to send? Kurtosis. Now, if I send these 4 words, okay, and again, this is before fax, this is for mobile phone, right? Just have 4 words. Somebody at the other end can roughly draw the shape of the distribution. So if you think about it, these descriptive statistics are like numerical summary. Okay. So that's a good way of thinking at it, right? I want to know about how tall people are, the high distribution of people in the Netherlands. I take 100 of them and I take the numbers. I can't send 100 numbers. I don't have emails, right? I just have Telegram, and Telegram is very expensive. So I'm going to send 1 word. Okay, and that word is average height, the mean. Okay, now, so in some other instance, if it's about income, maybe I won't send the mean, I'll send the median. Okay, but okay, let's say population of height of a human population. Take the mean, first word, second word, standard deviation, third word, skewness. By the time you have these 3 words, you should get a rough idea of what the histogram looks like without sending the actual histogram, right? Okay. So is this just something that is important historically? No. The reason it's not just important historically is because, remember I told you about all these 300 distribution that mathematicians define? Yeah. The reason they define so many of them is because each of them have different combination of skewness and kurtosis and shape and stuff. Okay. So that's why, even though right now we talk about descriptive statistic, when we get to advanced stuff like inferential statistics, where we get to actually fit individual function, this concept will be important. Because when you're trying to match the function to the histogram, how would you do it? You would do it by matching the mean, standard deviation, skewness, kurtosis. Conceptually, okay? There's some other algorithm. So think of this again. Let me say it again. You gather 1,000 Dutch people, take their height, right? Take an average, send that number. Okay. Take the difference from the average square, average that, send that number, or take square root of that if you want. To the power 3, send that number. To the power 4, send that number. If you send those 4 numbers, somebody at the other end can almost draw the distribution, the histogram. Now, when you get to advanced world of inferential statistics, you're not just drawing the histogram, you're trying to fit. But out of 300 probability distribution that mathematician came with over the last 300 years, which one would you choose? You would choose the one that fits the mean, standard deviation, skewness, and kurtosis. And out of those thousands, I just told you that there are about 10 of them that are the most useful. Okay? You cover your bases. Okay? So that's the name of the game. So please understand that is the name of the game. This is why we build probability first. Okay? So that's the concept. Now, how do you work with probability? In Mathematica, this is super easy. Okay? Okay. Now, I'm going to do this. This is my little table. It's sort of like give any distribution. So now I'm going to go to the Wikipedia page. I'm not going to go because it takes too long to switch. But let's say I go to individual in the Wikipedia page, right? I pick up one distribution. Okay? Actually, we could. We don't have Chrome. Okay. We have Bing. I don't use Bing, but go ahead. Okay. Wikipedia. Let's say normal distribution. Let's go binomial distribution. That's more fun. Okay. So let's go to this. Why is Indonesia? Why am I getting Wikipedia Indonesia? It's so smart. It knows you guys are sitting here. Too smart. Okay. Okay. Watch this. Now I'm going to do this really quick. And hopefully, as a reward, somebody will get that. So I'm going to switch again. Switch here. Oh, switch here. Right. Now I have to stop share here. So this guy shows up. Share screen. Well, I'm getting good. Okay, good. Now, this is fun. I always like to do this. I toss a coin, get tail. Oops. Tail. Okay, get tail. Okay, I toss again, I get 2 tail. Okay, now, what if the first time I toss, I get a head? Okay, right? And second coin toss, I get a tail. So if I get a tail here, if I get a tail here, it's gonna be tail, but I have a head on the bottom. If I have here, tail and a head, I'm gonna have a head and a tail. And I've got here, I got tail. Okay, oops, okay. Can you guys see this? Okay, can you guys see this? Right? Now, if I toss 3 times, I get tail, 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 right? Or I can do this, I can get tail, 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 head, right? And I sit here. Oops. Okay. So, okay, I get head, 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 tail, tail, and then head, head. Okay, you guys see this? Yeah. I tossed the right. So I toss the coin 3 times. I get tail or head, tail, tail, or tail head, or head tail, or head head, right? So these are all basic event, correct? These are all basic event, right? By the way, if we talk about basic event, the probability are all equal. If they are, well, in this case, if head and tail have symmetric. But if the coin is slightly bent, right? So that tail and head, it's not, then the basic probability are not the same. So for example, the left-hand side here, 0.4 times 0.4 is not going to be the same thing as 0.6 times 0.6. Okay, but the concept of adding probability is the same. Okay, so if I define this as my basic event, but I define my combined event as the number of heads in a given number of toss. So what is this event? 2 coin toss, 1 head, 1 tail. What is this event? 3 coin toss, 2 tail, 1 head. Right? Right? So if I have this probability P of getting a head and 1 minus P for getting a tail, what's the probability here? It's 1 minus P 3 times. Right? Right? So what about here? It's P 3 times. Right? Right? And what's this? Well, actually, oops. Why is it blur? I just made it dark. I didn't mean to. It's a bit dark. Okay, maybe here. Right? So this here, I'm going to have 1P and then 1 minus P squared. Right? And how many do I have? 3. Right? Right? So, same here. I'm going to have P 2 times, 1 minus P 1 times, and I'm going to have 3 here. So the coefficient is the combinatorics, is the combination, right? Right? And that is the binomial or Pascal triangle that we talk about. So let's go back to to Wikipedia. Stop share. Share. Right. Share here. And share here. And I go to here, you will see that if let the random variable x be the number of head in 3 coin toss. Each coin toss has parameter p of being a head. So there are 2 parameters, right? One is the p for the parameter of the probability of a head, and 3 for the number of times. Now, let me ask you this. What kind of sample space is this? It's finite, right? Because the number of head can only be 0 or 1 or 2 or 3. 0, 1, 2, 3. That's it. That's it. You just don't know what the probability is, and the probability is given here. See? P, the NK, that's the factor in front. Okay. So this is how mathematicians play with the game. Because there are 2 terms, head or tail, but you combine them, they call this binomial distribution. Now, for a single coin toss, it's actually called Bernoulli. Yeah, called Bernoulli. But, okay, so that's it. Now, obviously, a lot more will be in the center, right? You can see that, right? So this is why you get distribution that looks like this. Okay. So, how about this? How about you take a coin toss, right? A coin toss, and you want to know if right now, in the example I gave you, I'm the god, right? So I decree that the probability P is equal to 0.56. But once I created this data, I created this coin, you go play with it, you toss the coin 1,000 times, okay, let's say 1,000 times, then you get this kind of histogram. Your job then is to say, if I knew that n is equal to 1,000, and I get this histogram, what's the P? That is inferential statistics. Okay, so you can see this binomial construction. I hope it stay with you for the rest of your life, because it stayed with me when I was, your age. You build up the probability, right? I know the rule of the game. In this case, sort of like God said, I use a coin. But what God didn't say was, what's P? Okay, that's still a secret. Okay, but I gave you the coin, and then you toss the coin 1,000 times. So at least you know one parameter, which is n. N is the number of coin toss. N is 1,000. Okay, and you toss the coin 1,000 times, you get one value. The thing is, you only get one value. So instead of tossing the coin 1,000 times to get one value, you have to do it another 1,000, another 1,000. Okay. So maybe, you don't have to go to 1,000. Maybe you just go to 5, but you have to go to another 5, 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 another 5. And then you get the histogram of that. And then you ask, what P would have generated this? And you infer the mind of God, so to speak. I create the game. Infer the mind of the problem maker. I created the problem. That is inferential statistics. Okay. Now, this sounds very nice. Sounds very nice. But there's another thing that you need to know, which is a little bit confusing. And this is where we come in here. It's the concept called sampling distribution. Okay. Again, think of it this way. There's some random event. You kind of ask yourself, and I'm going to say this is the two things that you ask. Again, this is about if your project is about this is your statistical term project, right? As opposed to machine learning. How are data distributed? How are data distributed? That's question number one. So how are they distributed? You get the histogram, but you don't want to just draw the picture. You want to fit it with the mathematical function that best fit that histogram. So that's one question. And when you did this, you have to know what the function to choose and then get the parameter from the data. So that example that I told you was a little bit too easy because when I told you that you just do the coin toss, I just don't tell you the P. At least you know it's a coin toss. And if you know it's a coin toss, you know it's binomial distribution. Okay? You don't think of anything else. Okay? You don't think of any other 9 or other 300 probability distribution. But in your life, if that's your project, that first step is not so obvious. So you have to choose the function, then estimate the parameter. Okay? So that's called distribution fit. Okay? The second thing you want to know is you want to know something about certain the mean of that. So this is sort of like going back to that telephone thing where you have the data and you're trying to find what the mean is. That's too simple. But there is a lot of questions that you can build around the means. So instead of asking what's the mean height of people from the Netherlands, you can ask some question like, are the mean height of people from the Netherlands different from those of the people from Denmark? And you can ask all kind of complicated questions about the means. So when we move, and I'm going to move right now to inferential statistics, right? There are two kinds there are a few kind of questions you ask. First kind of question is, how is the data distributed? Second kind of question is, you have a different kind of population. You try to test, are the mean the same or different, or just one of them, or maybe this one is bigger than the other, blah, 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 right? And then you can ask something else about, if I knew X, can I know Y? That's regression. So those are the questions that we are going to move into, right? But before we move into, and before we go to the break, let's start working on probability side, but using Mathematica. Okay? So again, bear in mind, we're going to take a break shortly. When we come back, we're going to go statistical inference. And statistical inference, again, you're going to ask questions like, how is the data distributed? What function best fitted with what parameter? Then you're going to ask a lot of questions about the means. Like, is the mean bigger than 5? Or is the mean of this population, subtract the mean of this population, bigger than 3? All kind of stuff about the means, okay? So it's not as detailed as distribution, but it's more practical because you're asking about many populations, so to speak, okay? So if you have one population, you focus on the shape of the distribution. But if you have many populations, sometimes you just want to know if the means are different. Does that make sense? Does that make sense? Okay? Right. So a good example would be in medical. You have two populations. You don't really care about describing the shape of each population. You just want to know if they're different. Because one population was given placebo, the other population was given real drug. And you just look at recovery time. You're not trying to fit recovery distribution time. No, you don't care. You just want to know if this group recover faster than the other group. Okay? So those are the sort of question you ask. Okay? And then the final question would be regression kind of question. If I knew the blood type, I knew the sugar level, blah, 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 how bad or how long is this guy going to live with diabetes or something like that. Okay. Right. I like to give my example in sort of like medical thing because I think most of you are keen to go into health and well-being, right? Concentration. But you know, I'm not from that area, so my example would probably sound a bit silly to most of you. Anyway, now the only thing I'm going to mention now is that there's this thing called limit theorem. It's one of those things where it doesn't matter what original population is, but if you sample a whole bunch of them, the distribution of that sample will be around the middle and it would have a normal shape. So this is a subtleties that I think a lot of probability and statistic people miss. You have many kind of probability distribution. One of which is this shape called normal distribution. But that normal distribution is so special because on its own, it's already a very good distribution to use. But if you take, instead of taking one human being, okay, so let's say, let's do this. You know, right, that the income very skew. Income looks like this, right? Right, income very skew. Definitely, would you use normal distribution to fit income? No, you would not. However, if you take 30 people at a time, ask for their income, keep that as one data point, ask another 30 people, take average of that. So the distribution of the mean itself, if you plot histogram of that, you will get a normal curve. That's why normal distribution is so important. Not because it is a nice looking distribution, but because due to mathematical reason, it's the distribution of the mean, regardless of what distribution the original population is. Okay, that makes sense, right? If you think about it, let's say I have a distribution that looks like this. Watch. Is a distribution that has a lot of short people and tall people. Okay, not like the orphanage. Let's say I have a room full of very tall people and very short people. So the distribution of that is going to look like this, right? Right. But if I take 10 at a time, take an average, I'm going to get some short, some tall, some short. I take another 10, or let's say take 30, 1 point, another 30, 1 point, another 30, another point. That distribution of the sample is called sampling distribution. That one is going to be around the middle and it's going to pile up like a normal shape. Okay. So this is what we would use to ask all kind of questions about the mean. Okay. So they actually, when I was a student, I can do, you know, all the calculation, but I never quite stood back and said, you know, there are actually two kind of track in classical statistics. Now that I realize that, you know, I'm telling you. Okay. So again, you can scrutinize individual fit, trying to get the best fit. That's one thing. But if you're trying to test population, you don't really care about shape. You just care about whether or not they are located at the different means. Okay. So you can ask some practical question like, if I gave this guy drugs versus placebo, does he recover faster or not? Okay. And I don't care about the distribution recovery time. I just say, on average, is it better to take the drugs or no different from placebo? Okay. Right. Okay. Okay. So let's go to Mathematica to show you how it works. Very easy. Now, all kinds of probability. I'm going to give you this thing here. Okay. So I'm going to go to the example. Where are we? I can't find it. Okay. Now, okay. This is actually, now in Mathematica, it's very easy. In fact, I don't have to use this node. I can just start from scratch. New notebook. Okay. This is my distribution. Okay. I'm going to toss the coin 10 times. Binomial distribution. Okay, type it. Binomial distribution. One word. Now, again, go to F1. Oh, not F1 here. Kills everything. Oops. Yeah. What did I do? Okay. You go to F1. Can you do that? It goes to the help page, right? I suppose it kills everything. Okay, I don't know. Okay. Well, is still recording? Oh, okay. But I have to share, right? Oh. Okay. You do that? Anybody? Yeah, you can use it, guys, because you can use F1 during the exam. Yeah, I know the distribution. Okay. So what's the first line say? Right? Say how you use it, right? If you have to add, it's expecting how many parameters? 2 parameters. What's the first parameter called? N. N is the number of coin toss. What's P? P is the probability of hit on a single coin toss. Right? Okay. Now go down to the example. So you can actually replicate the entire Wikipedia page here. Now, the way it's done is, remember I told you that Mathematica is like a functional programming. You have to communicate by way of function. The function that says binomial distribution, open bracket, it says n and 0.5. That only declares, that function is a declaration function. So it doesn't produce anything. It's what it's doing is it's receiving instruction from you that I want to be working with binomial distribution n equals 10, p equals 0.5. So you did that and then you shift enter the rest of the minute. Right? But this is where it becomes powerful. Once you declare that this is what you want to play with, you can add all kinds of stuff. So in Wikipedia, yeah, well, first of all, this is common sense, guys. If I toss the coin n times, each time have a probability of hit of 0.55. What is the expected number of hits? 5.5. Right? Remember, the expectation is not the same. So you don't get 5.5 hits, but the expectation is 5.5. How do you get that number? It takes n times p. Right? So in this case, okay. So if I'm just gonna define it. Okay, 10, 3. Okay, so it does nothing. That's nothing. Okay, so I'm gonna call it my distribution. Okay, my distribution. That's it. Doesn't do anything. It just say I'm gonna be working with it. Now you can say, what is the mean of that? Okay. Right? don't know why. Hold on. Okay, this is what I would write. So, well, I can do mean first. I don't know why it doesn't say. Oh, distribution. Oh, sorry. Point. Okay. Yeah, sorry. Point 0.56, right? I think. Yeah. The reason it gave an error is because P cannot be bigger than 1. Okay. Silly. Okay. So that's that, right? So what's the mean of that? 5.6. Okay. What is standard deviation? What is skewness? By the way, skewness. So these are kind of like statistic you can draw, right? Now, what if I want to draw the distribution? Okay. What if I want to draw the distribution? Now I can use my this, but just so you can start from scratch, you can say something like this. Okay. PDF is that PDF stand for PMF as well. In probability, if it's discrete, it's called PMF. If it's continuous, called PDF. Okay. But anyway, in here you just use one command, PDF. Okay. My distribution. Okay. X. So this is the function. Okay. The reason we write it this way is so that the PDF can refer to any kind of name distribution, and you just give the name here. So if I didn't define it before, I can do this, obviously. Okay, type this. This is what you have to do on exam, guys, so get used to it. So I want the PDF. You remember that in the Wikipedia page, I want to draw that, right? So PDF of this distribution with respect to X, right? I want to plot it. Now, I'll tell you this, it's called discrete plot because it's a point, it's like a table. Okay, just something you might not know. Okay, and X between, now, if it's between, if it's binomial 0 and 1, what's the range of X? It can't be smaller than 0, right? It can't be bigger than 10. So I might as well, if I did this, minus 10, minus 5, and 20, okay, it's not going to give you anything because it's just going to give you this, right? Because instead of complaining, it could complain that, but it's not valid. Instead of doing that, it just gives 0. Okay. So actually probability start here, right? Okay. Right. So let me do this. Again, in your exam, not only will you be tested on probability statistic, you'll be tested on interactive visualization. So one of the things that you can do is, how about we vary the P? All right, so copy that, put it down here. Okay, put it down here. And I say, well, instead of this, let's make P a parameter. Okay, and I manipulate P between 0 and 1. Manipulate. Okay, so start at 0 and right. Okay. 0 and 1. Now, how about n? Tell you what, I know that this is going to be 0 and this is going to be n. How about manipulate n too? Let's manipulate n. Okay. Now, here's tricky. N cannot be continuous, right? So it has to be integer. So let's start from 5, go to 20 instead of 1. Okay? So 5, right? P is equal to 0. So see, if P is equal to 0, everything is 0. If I make P bigger, right? Can you see that? Hold on. Let's control placement on the bottom. Okay. All right. There we go. See? What if I want bigger n? Right? Right? Okay. Now, PDF is a probability at a point, right? In this case, it's PMF, probability at a point. But what if I want cumulative probability? So CDF. Now it's going to look like this. Now CDF is a regular plot, so it looks like this. It's not discrete, and right. So something like that. I can add something like filling axis, so that looks a little bit more colorful. Okay. I can make default P at 0.5. Let's make a default P. Let's make it 0.5 and N start at 10. So it's more interesting. Again, now this is interactive visualization of a probability, not of the data, right? But if I'm testing you on this, you can do that, right? Okay. It looks, difficult, but it's not. Trust me, if you were to do this in other language, C or Python, you would already take 50 lines at least. No, more than that, because the interactive takes another 100. Okay, but in this case, you have 5 lines. Okay, so plot CDF of this distribution. Okay, for example. So this is something you can do. Okay, now, and now this is something I want you to remember. Can I do this? Escape. DIST escape. Do you get this? Try that. Escape. In Windows, you can do this. Escape. It's a shortcut. DIST escape. Can you get that? People with MacBook, can you get that? Okay. If not, you can do this. / open distributed. Okay. Distributed. Okay. Same thing. You get this symbol. Now, my question is, okay, let's go back to PDF. Okay. And PDF is a discrete plot. Okay. Now, I want to know what, if this were the case, what's this probability here? Now in Mathematica, it's very easy. You just ask. Okay. What's the probability? Okay. X. Now you can use little x, but technically it's big X. X is equal to 2, given that X is distributed according to binomial distribution 10 and 0.5. That's it. Okay. And it gives you all kind of calculation. Again, this is one of those one-liner that in a general language, low-level language would take you half a page. Okay. So all it's saying is, given, okay, this, that X has X, when the right statement say, let X be a random variable corresponding to 10 coin toss, where each coin toss correspond to the value 1, and you just count how many heads, right? So that was the case. What's the probability of getting 2? What's the probability of less than equal to 2? What is a probability getting X less than equal to between 2 and 4? Okay. All right. So for, I think, one guy who's doing project in probability, what you do is you get data set. So let's say you're working with, let's make life interesting. Let's say sustainable development, and you worry about water pollution. Okay. And you get data of water pollution reading or PM 2.5 reading. Again, this is data analytics, right? So you should be able to get real life data. So let's get PM and PM 2.5 data for Bangkok. Okay. You fit that distribution. So that's the distribution of PM 2.5. And let's say the doctor came up with the recommendation that you have high risk. All people have high risk if PM 2.5 is greater than, I don't know what the unit is, some number alpha. Okay. So what happened? What would you do? You would do exactly this. What's the probability X is equal? So you would say something like this. So you get data. So you get some data. Okay. Once you get data, what do you do? Fit it and call it DIST. It's my distribution. Okay. So what would you do? You would say something like, what's the probability X is greater than, I don't know, some alpha 0.567 or something like that, given that X is distribution. Okay. Right. And that will be your warning. Okay. That will be, and you can produce a table of this. You can produce a table that say, okay, what if this threshold is a function of age? So this is kind of like some threshold and then age, right? What can you do? You can manipulate this. Okay. And probability of this, and then something like age from, I don't know, start from 10 to 90, right? See? All of a sudden, you turn public data on PM 2.5, add to it medical recommendation of a risk hazard for people of certain age, Okay, so I'm just making this up again. I know nothing about, about health science, but let's say that old people are more vulnerable for lower count or something like that. Okay, so this is a probability that matters for different age group. Okay, so you get this and this distribution, and maybe this distribution is itself is a function of some factor like humidity. Okay, in which case you have distribution of PM 2.5 as a regression function on humidity. Okay, that's it. That's the entire term project about using data analytics on real life data using statistics. All right. Now, I haven't talked about a regression yet, but let's say you have regression. So you have regression equation of PM 2.5 as a function of humidity, temperature, time of year, whatever. Okay. And then you have a table recommendation from the Medical Association of Thailand or whatever, the World Health Organization. What is the threshold as a function of age, or maybe condition, like people with diabetes, maybe less, people with tuberculosis history may have a lower threshold because they already have bad lungs. So people with COVID, right, as opposed to non-COVID. So in which case you have another option that say something like comma, COVID history and true or false, right? Right. So in this manipulate, the user can say, oh, I have COVID history. I click yes. I am 35 years old, 35 years old. Today, I live in Bangkok. What's the probability tomorrow is going to be a bad day for me in terms of PM 2.5, something like that. Click. All right. Something like that. Okay. I can make an app that say, well, because I'm very, I have a bad history of I have terrible lung. Where I go is very important. So I'm not going to go to place with high PM 2.5. So if Chiang Mai has high PM 2.5, I'm not going to go. So I connect this with my booking app. I don't know. It's all kind of silly stuff you can do. Okay. That would be your data analytics kind of project. Okay. It's that kind of bringing things together, data, model, real number, mathematics, interactive visualization, interface design even, right? Application. That's a sort of integrative creativity that I want to see in you guys, in Basai student. Now, what distinguishes this from, say, the majority of the project I'm going to see in this term is because right now the tools is probability and statistics, right? But what if the tool, instead of regression equation, you use like decision tree? Then that would be a machine learning kind of project, but similar kind of environment, right? Okay, so with that, let's take a 5 minutes break. I don't want to take too long a break because we have a lot to go to, okay? When we come back, I'm going to move to the statistical inference side and then show you again how it works with Mathematica. Again, it's probably 3 lines, 4 lines, okay? But so you get what we've done today, right? Probability, okay? Let's agree. Probability has intuitive definition, but we tend to work in terms of frequency, getting sample of data so that you can use this to infer what happened with the real population, right? With probability, you have to decide first on possibilities. You have to know the set of possibilities. In other words, that's called sample space. Once you decide on that, right, then probability is about filling in the height of that probability. Okay, how do you do it? You can derive it from this kind of game, right? It's coin toss. But to be honest, mathematicians, you know what they did? They are given free hand. Say, give me any function that is non-negative. And over the sample space, another word is called support, the value add up to 1. No wonder in the last 300 years, we have got 3,000 probability distribution. It's like innovation game for mathematician. right? If you want to make a name for yourself, okay, you just say, oh, I just come up with some function that is non-negative. If it's discrete, add up all the height to 1. If it's continuous, you don't add the height. What do? You use calculus, right? Integrate area. Okay, so that's the difference between discrete random variable and continuous random variable. Discrete random variable, the probability are like sticks. You add up the height of the stick, it has to add up to 1. If it's continuous, it's sort of like a hill kind of thing, and the area has to integrate to 1. That's it. If you create a new function, new mathematical function, you can name it after yourself. Now, you would only be famous if in real life you have that combination of kurtosis and skewness and shape and, that looks like some real world data. Okay? Now, normal distribution is very different because not only is it there as a candidate to choose, it's there as a default distribution if you're studying the mean. Normal is the only one that's like that. Actually, there's student T as well, but that's a special case. But everything else is like just a brand. Okay? I created the Dirichlet distribution because my name is Dirichlet, so I name it after myself. And for some reason, it fits the data. I become popular. People remember me 200 years after my death. Okay? So if you want people to remember you after you're dead, okay, create a new probability distribution function, name after yourself, and hopefully there's some data set that fits, and that data set is really important in business. Okay, but I would bet against it because most of the useful ones have already been discovered. If you invent something else, it's likely to be variation of the old one. Okay, so take 5 minutes break. We're going to